implement this. You know, I have one neuron, I have second neuron, each row is a neuron, right? And if I have one neuron, the output will be only one value. If I have two neurons, the output will be two values, right? So I just leave this. Let me using a real world task, the Titanic task, right? I already introduced the Titanic task, right? We have three features: the gender, the Tiki class, and where the people embark on in Queenstown of the southern town. I use these three features to predict whether the passenger will survive or not. So I do the train split. So now let's use neural network. Okay. Let's create one layer of neural network. So one layer, I have three features, right? Now I want to transform these three features to two values, to two activations. So in this layer, I have a weight is, I don't care about the number of weights, as Margaret asked me the question, where the weight come from. I don't care about that, just any values. Here I use a normal distribution to generate weight. What's the dimension? As you can see, I want to have two neurons. So the number of rows is 2, and what's the number of column? The number of column is for feature, right? The first column is for the first feature, the second column is for the second feature, the third for the third feature. So that means I can say X trim the shape 1, right? X trim is a data matrix. The number of column represents the number of feature, right? So that's why I use 1, right? The 0 means the number of rows, right? So I use the number of column. I have some B here, you know, you have some bias turn, that's okay. So you have two neurons. For each neuron, you should add plus B, right? W1 x1, W2 x2 plus W3 x3, then you plus B. That's a linear function, you know that, right? Then we can use this to transform your data. You can W extreme. I want to make it 2, 1. So then it will do the matrix broadcasting. Just don't care about too much about, you know, some broadcasting things. I will reshape this in some way to make the, you know, matrix computation work. So you don't need to care about too much. You just know, okay, this is a Bayes tensor for linear function. So I have a 2 linear function. So that's why I specify 2. That's okay. So I have plus B. That's it. But what do we left? We left an activation function, right? So I want a sigmoid function to be activation function. So I just call sigmoid on Z. Now I have a, you know, I have a, let's say the dimension 627. This 23. This is the number of training example, right? We have this number of training example. Now for each examples, before we have 3 features, right? Now I put these 3 features to one layer, neural network layer. Then this neural network layer will generate 2 values. As I said before, the 2 values are called activations. So that's why I said A here. But in neural network we have not only one layer. We have 1, 2 layers, 3 layers, right? And now just make another layer. I will call this layer 1. So I should give 1 here, 1 here, 1 here. This means this is layer 1. This is output of layer 1. This is parameters of layer 1. Then I run it. Then using the sigmoid function to really generate the output of the outputs for of all the neuron in this layer. Now I go to another layers. In this layer, my input is two features, right? Here is two features, and I want to make this two feature to only one. This one is the final output. This is the probability of choosing the class one. Okay, one means this passenger survive. Okay. Okay, let me do this. What do I do is this one is the output dimension. This one is the input dimension. This two is input dimension because we have two feature here, right? So now we have B2, 1, 1, right? Because we only have one neuron, so only have one bias turn. So now we apply the linear, not linear. Yes, we apply the linear function here. Then we apply the sigmoid activation function here. Now we have the output. Okay, this is the probability of being being class one, right? I just define it in this way. So okay, we finished. Now, what's the difference with logistic regression? The only difference is just this. It's just I have another layer, right? If this is a logistic regression, what do we have? We only have one layer. So if we only have one layer, so what do I need to change? What do I need to change is I don't want to output two feature, right? I only want to output one values to represent the probability, right? So now here is not two, here is one, right? But now I have two layer. I go from three feature to two features, then go to one feature. This one feature represents the probability of being survived or not. Yep, that's it. But in logistic regression, we don't have this. That's it. We just have 3 to 1. Oh, good. Any question for this processing of neural network? You can ask me the question in the chat box, but I want to show you that I want to make the prediction using this randomly initialized neural network. Of course, it doesn't work, right? Because the weight and bias doesn't train on the training data, doesn't optimize on the training data. We just randomly initialize it. So if I say, okay, this is the probability of a passenger being survived, it shouldn't give me the good result. So let me show you. It doesn't give me the good result. I think I can, yeah, let me copy paste this code to do the prediction on the on the test data. So activation, okay, this is just a probability. So right, if it's less than 0.5, I make it 1. So that's why I say I type in 1 means okay, they survive. These people survive. So then I calculate the accuracy using this. You don't need to. If you don't, you feel a little bit confused about how this gave me the accuracy. Just trust me. This will give me the accuracy. So let's see the results. Okay. It says it's not matched because here I gave the training data, right? So now I give the test data to do the processing. Number of test data equal y hat. This is flattened y test, x test. Let me ensure the dimension is 268. Okay, that should be correct for the processing, but here is y height doesn't equal to, let me print the dimension of A. Oh, so the problem is the dimension of A, right? It's not the dimension of training test data. So let me have a look. This is a test. Oh, good. I do wait here. Okay, so the problem is here. I should, okay. Three, shape 3. This is 1, 3. Let me print this. Oh, shape. Oh, okay. Y height is 3. Now it's oh, okay. Because I say 1, I should say the number of examples, not the number of features. Because yeah. Oh no, I should processing this training data. Why I says the dimensions? That's stupid. You know, it's just you use the weight to multiply by your data, right? That's a linear function. So I shouldn't give the dimension here. I should give the data here. Now it should. Let me redo this. Test data. 2, 3. Here I have for 2, 3. Do the dimension here. You say it's always when you do really code something, it's always harder than generally understand it. Okay, now it shouldn't be. Yep, now it work. You can see the accuracy is 58. You say it's not good, right? It's basically random. If we take random choice, we have 50% accuracy. Now it's a little bit higher than random because that is also random result, right? Okay, so any question for this so far? If no question, the next step is to use gradient descent to get really good result to train the neural network. No question? Okay, so let me go forward. Now, let me rebuild this neural network because here I just do separate processing, right? I wait here, then I process it, then I generate new weights, I process it, right? I want to generate a weight together. So now I give the, okay, what's the number of features in original data? So what's the output neuron, number of output neurons in each layer? So as I said before, I have 3 features for the Titanic data set. Now I go to 2 feature, then I go to 1 feature, then finally I finish. Okay, so that's why I said, okay, the first layer I have I want 2 neuron to generate 2 features. The last layer I want the 2 neuron. Oh, sorry, I want only 1 neuron to generate only 1. I call it feature, but you know what I mean. It's just 1 value, right? You can also take it as a feature, something like that. It's just a term because feature is just means reflecting some perspectives of the data of the example. But normally in the science, people will use a feature as an input for model. But here you can also take it as a feature. I will say it's a feature, so it doesn't matter. Okay, so now I can generate weights for different layer. Okay, so so it's a list for this list. The first element is a weight for the is a parameter for the first layer. The second element is parameter for the second layer. So for the first layer, it's just this, right? For the second layer, it's just this, right? Here I use normalized normal distribution to generate the to randomly generate the parameter. Here I use the uniform function. That's the only difference. Otherwise, it's all the same thing. Okay, now let's generate the weights. Okay, I generalize the weights. If I apply this weights to to do the prediction, actually it also give me the bad results. Same thing like this. I won't try it here because you can try it. Actually, you don't need to try it. You can believe me, right? Because it's just randomly initialized weights. Why it can perform well. So now I will show you how I can optimize this W and B using gradient descent. So you remember gradient descent? I don't care about the initialized weights and bias. Just give me randomly. Then I will calculate the gradient of weights and bias based on the training data, right? Then based on this training data, I can get the gradients. Then according to the updates rule, I will minus the, this is just equal to weight minus learning weights multiplied by the gradient, right? So this is a last layer. So that's why I also get the weight gradient for the last layer. This last layer, gradient for the last layer. This is the second layer, gradient, second last layer. So gradient for the second last layer, gradient for the second last layer to update it. Then update it in 1,000 iterations. Then let's see the result. Now I have new weight, right? Now I use this new weight to do to predict predict on the test data. Remember, these weights are optimized on training data, and now I evaluate on the test data. Makes sense, right? Let's see the result. Boom. See, almost 80% accuracy. So amazing, right? It works. So if you go to the deep learning unit, you will learn how to calculate the gradients, because you can't manually calculate the gradients, right? It's too much work. You have multiple layers, you have multiple neurons, you have 1,000, 1 billion neurons. So you have to automatically calculate the gradient. Yep. So actually, I think it's if I have time, I can just show you how I can automatically calculate the gradients. But just let me give you a full picture. If you want to go into the detail of the neural network and deep learning, what's the directions? One direction is figure out how to automatically calculate the gradients for all the weights and bias, for all the parameters on different layers for different neurons. And another direction I already tell you, this gradient descent is very naive. We can you already in week 10 assignment it requires use RDEM. I already said what's RDEM. One important thing is don't use the fixed learning rate. This learning rate is fixed, right, for all the iterations. So I can define it outside the loop. So but for other advanced neural network optimization deep learning, you need to make the learning rate dynamic. It's a second second things you can change. And another thing you can change obviously is objective function, right? Here I just use a naive objective function. I don't use in regularization. You can add the regularization on it. You can actually how I reflect is reflected on this. This is gradients with respect to the objective function of the maximum likelihood optimization is y log y height. This is a gradient of the prediction with respect to this. Actually, I already manually derived this at the week 6 workshop, so you can have a look. Actually, this equal to y height minus y, and divided by the divided by this. Okay, so you can go to the if you are interested in how I manually calculate this, you can go to the week 6 workshop. Then you will know that. But as I say, the first point in deep learning, you have to automatically calculate this. The second point is you can have adaptive learning way. The third point is you can add some regularization. And there are many other points. The first point, fifth point, I won't describe all of them here because this is another unit called deep learning. So if you are interested in this, go to deep learning to learn the details. Okay, I think I just finish here because I think it's already too much for you. But if you are interested in some kind of points like how to use how to automatically calculate the gradients for all the weights, how I can adjust the learning rate, how I can add the regularization. Yeah, you can just ask me. I still have some time, so I can just go into a little bit details. Otherwise,